Now, if you move on to the notes, page 1, this was the part I haven't really gone through with you guys. Now, in the first lesson that I had with you, I defined for you what was oscillation, where I tell you that it is actually repeated back and forth motion on either side of an equilibrium position. And then from there, I mentioned to you that oscillation has a very special kind of oscillation called simple harmonic motion. Simple harmonic motion is actually just a very special kind of oscillations where A is proportional to X and A and X are in opposite direction. That was what we went through recently. Now, when it comes to oscillations, you can classify oscillations in general as two types of oscillations rather than simple harmonic motion. You can first classify oscillation as free oscillation. Okay. Now, what is a free oscillation? In free oscillation, a system will just oscillate after being given an initial disturbance. That is what free oscillation actually is. The simplest example of free oscillation is your pendulum bob that you see here and the mass on the spring that you see here. You would understand that if I were to displace the pendulum bob a little to the side and then release it, it will start to oscillate by itself without you having to continuously push it. The same goes with your mass on the spring. You just displace it a little and then you release it, it will oscillate up and down by itself, right? You don't need to purposely keep on pushing it so that it oscillates, right? So this is what free oscillation actually is. In free oscillation systems, you really only need an initial disturbance, okay? A periodic external force is not required to maintain the oscillation. Periodic here means at regular time intervals. Okay, that's what periodic actually means. Periodic external force means force being applied at regular time intervals. Okay, so this one, let me just write it out. Okay, you do not need to apply a force periodically to have free oscillation. Now, when an object is undergoing free oscillation, it will have a certain frequency of oscillation. That frequency is called your natural frequency. Okay, any object that is oscillating by itself, that's experiencing free oscillation, the frequency at which it's oscillating is called natural frequency. Okay, so when it comes to the definition of natural frequency, which does come up in your exams, the easiest definition for people to understand is that natural frequency is the frequency at which a system oscillates after being given an initial disturbance. But more specifically, the marking scheme uses the second definition. They say it's the frequency at which an object oscillates when there's no external force acting on the system, which is kind of true. You see, when you go and displace the mass or whatever object and you release it, it will oscillate. So during the time it's oscillating, it is correct to say that there's no external force acting on it. You did not actually purposely apply a force to cause it to oscillate. And if you assume that there's no resistive force acting on the object, and if you assume that there's no resistive force acting on the object, this is actually free oscillation. Okay, so the second definition is actually the one that the marking scheme uses more often. The first one is not something that I've seen in the marking scheme, but it helps people to understand it better. Okay, but for definitions, I would suggest you use the second one. All right, is the frequency at which your object is now oscillating when no force acts on it. Neither driving force, neither resistive force. Okay, so another example of free oscillation system could be when your guitar string is plucked, it starts to vibrate by itself. So when it vibrates, it's vibrating as its own natural frequency. Okay, now one thing I should also kind of mention to you is this. When you have a larger initial disturbance, you will cause a larger amplitude of oscillation, but it actually doesn't alter the period and hence frequency of your oscillation. Instead, what will happen is that the oscillating object moves faster so that the period remains the same. So what do I actually mean by that is something like this. If say I have a pendulum bob again, this one, if I were to displace it by say my initial displacement is 3 centimeter, and then I release the pendulum bob, yes, I know that the object will oscillate back and forth, but the maximum amplitude would also still remain at 3 centimeter. Just now I explained at length just now why it will never be more than your initial displacement. Okay, so if I give you an initial displacement of 3 centimeter, your maximum amplitude will just be 3 centimeter. It can never be more, but it can be less if you have energy losses. So say I have the same pendulum bob again, but this time I give it an even larger initial displacement. Maybe say this time I give it more than double my my original displacement. Say now my initial displacement is now 7 centimeter. So it's going to be the same thing. When I release the pendulum bob, it will oscillate back and forth with a maximum amplitude of 7 centimeter. Okay. But the thing is that even though I've given both systems different initial displacements, which in turn results in different amplitude, the period should by right remain the same. If I tell you that the period here is 5 seconds, this one, the period will also be 5 seconds. Okay? So if you have the same period, you will also have same frequency. It doesn't changes. It doesn't change. But if your period and frequency doesn't change, what actually changed then? You know that your amplitude now is different, but something must have changed now. So what has actually changed is that your object is actually now moving faster so that your period remains the same. If you consider this, for the first system here, it took you 5 seconds to make one complete oscillations with an amplitude of 3 centimeter. But for your second system, because your amplitude is much larger, if you were to have the same period of 5 seconds to complete one oscillation, your object needs to move faster to be able to compensate for the extra distance that you have to move. Okay, so this is just one thing to take note of when you're talking about changing the amplitude oscillations of a system. If you go and make the amplitude or oscillation bigger for the same system, it won't change the period, it won't change the frequency. All you ever do is to change the speed of the oscillating object. That's all there is to it. Okay, so that one is all right. Okay, then one last thing that I should probably go through with you is force oscillation. Now, if you have something called force oscillation, if you have something called free oscillation, you also have something called force oscillation, which is the direct opposite. Force oscillation is an oscillation that's forced into motion by external periodic force. You actually have to apply a force at regular time intervals to cause the oscillation to continue. Okay, so you need to have continuous force applied. In other words, you need to have continuous energy input so that the oscillation can be maintained. Now, the frequency of your oscillation in a force oscillation system will always be the same as the frequency of your periodic force. Okay, so what is an example of a force oscillation system? Could be a case where you take your ruler. I'm sure you have a ruler around you right now. You take your ruler and then you wave it up and down. You notice that your ruler is actually oscillating. So let's just say this is you with your hand, and then this one is your ruler. If you go and shake your hand up and down, you will cause the ruler to oscillate up and down. Okay, so this is actually an example of force oscillation system. You notice that if you just stop moving your hand, your ruler stops oscillating. But the moment you start moving your hand up and down, the ruler oscillates. Okay, and the frequency with which your ruler oscillates will follow the frequency with which your hand is moving. If I told you that the frequency of your hand moving up and down is 5 Hertz, the frequency of the ruler oscillating would also be 5 Hertz. If you change your frequency of your hand to say 10 Hertz, the frequency of your ruler oscillating would also change to 10 Hertz. Okay, that's what we mean by the frequency of oscillation being the same as the frequency of the periodic force applied. Okay, the frequency of a force oscillation system is called forcing frequency. Okay, it's the frequency at which the object is made to oscillate. All right. Now, for all objects, one last thing I should kind of mention to you is that all objects have their own natural frequency of vibration, regardless of whether they are free or forced oscillation systems. Okay, so just now I mentioned to you that for free oscillation system above, when the thing starts to oscillate, it oscillates as its natural frequency. Okay, now for forced oscillation, your object also has its own natural frequency. Okay, just that it's not readily shown. Okay, I think I should add one other statement here. For free oscillation, the natural frequency of the natural frequency of the object is readily shown. Okay, one way to interpret this statement is this now. Okay, is by thinking of it as this. For free oscillation, your natural frequency is readily shown. You just need to let it oscillate, it will immediately show you your natural frequency. But for forced oscillation, it doesn't show that easily because its frequency will always follow the frequency of your forcing frequency. Okay, but here just understand that every object must have their own natural frequency, regardless of whether they're free or forced. Okay, so that one is okay. Then after that, I think I'll go through a bit of damping, since I went through damping with you just now. So just now, I told you already what is an undamped oscillation. Undamped oscillation is where you have something like this. This is what undamped oscillation actually is. Your amplitude is constant. But if you have a case where your amplitude isn't constant like this, where you see that your amplitude decreases with time, this is what we call damped oscillation. Oscillations in which the amplitude and hence energy decreases exponentially with time due to damping forces. Now, damping is the loss in energy of an oscillating system because of resistive forces, say friction and air resistance. Okay, so as your object oscillates, it could be rubbing on some surface, or it could be encountering air resistance that causes it to lose energy because it has to do work against these resistive forces. So when you have energy loss, your amplitude will naturally drop. Okay. Now, damped oscillations normally have amplitudes that decrease exponentially with time, not linearly. You see, if I try to trace the lines connecting all the amplitudes, it isn't a straight line, it's a curved line. This is what we mean by exponential drop. If it's a linear drop, it'll probably be something like this, where if you try to connect the amplitude points together, it will form a straight line. Okay, so for damping, your amplitudes do not drop linearly. It tends to drop exponentially. Okay, so that's just one thing to note here. Right, the statements below here, probably you don't need to know, so don't need to bother so much about that. Okay, now the one that we just really want to talk about is the types of damping. Okay, so types of damping, there are actually 3 types of damping that you need to know. The first one is called light damping. Now, for light damping, oscillations are always maintained about the equilibrium position after your body has been displaced. is actually this red colored line here. Light damping specifically still would have oscillation as the amplitude gradually drops. Okay. Then after that, you have something called critical damping and heavy damping. Heavy damping is this green line here. Critical damping is this blue colored line here. Okay. Now notice that there's a similarity between critical and heavy damping. You notice that they don't keep on oscillating. They actually just straight away go back to the equilibrium position. Unlike light damping, you see there's still oscillation about the equilibrium as the amplitude gradually drops. But for critical and heavy damping, you don't see any oscillation being maintained. They just straight away go back to the equilibrium position. Okay. Now, that's the similarity between critical and heavy, but there's a difference between those two. Critical damping usually returns to the equilibrium in the shortest time possible. Okay, you see this is the time for critical damping to return to equilibrium, but for heavy damping, this is the time that it took for it to return to the equilibrium. Okay, so this is the main difference between critical and heavy damping. It's really more in terms of the time. For critical, the displaced body returns to equilibrium without passing through it in the shortest time possible. But for heavy damping, there's no oscillation about equilibrium position. It returns to zero in a very, very long time. The return to zero displacement takes place very slowly, much longer than that of critical damping. Okay. Now, an example of heavy damping is the one that you can see in your classroom door. Okay, you're studying in Sunway. I believe you just observe your classroom door. This is your door, right? You notice at the top corner of your door, there's something that's attached to the door and the wall. There's a box looking thingy, and then there's some bar that's attached to the door. So this thing here, the purpose is that if you open your door and then you let it swing back, you release your door. This thing here is the one that causes your door to swing back very, very slowly to the closed position, right? So this is an example of heavy damping. You opening the door is an example of you displacing the door from equilibrium position. Then when you release it, it wants to go back to the equilibrium position, but you notice that it goes back very, very slowly because of this thing that you attach to the wall and the door, right? So that one is actually heavy damping. Okay. Now, critical damping is what you see in your cars. Oh, sorry, what you experience in your car. When your car goes over a bump, you notice that your car body will actually shake a little, but it doesn't continue shaking after you went through the bump, right? What happens then is that when your car went across the bump, you will feel that your car actually move a little, but then almost immediately it goes back to its normal position, right? That is critical damping. Okay. If your car is light damping, you will notice that once your car moves through your bump, it keeps on oscillating up and down. Okay, that is not good. What we want is critical damping for your car, so that once you go through your bump, your car body will displace a little, but then it goes back to equilibrium in a very short time. Okay. So I'll move on to the next part, which is resonance. Resonance is actually the major part of your oscillation chapter, in addition to simple harmonic motion. So what is resonance actually? Resonance, maybe I should just make the screen big. Okay, so what is actually resonance? Resonance is just simply a phenomenon in which a system will start to respond at maximum amplitude when an external driving force is the phenomenon in which the system responds at maximum amplitude to an external driving force when the driving force frequency is equal to the natural frequency of the driven system. This one actually just means this, simply put, when driving frequency equals to natural frequency, you get maximum amplitude. This is what resonance actually is. If you want to summarize it, is when driving frequency equals to the natural frequency of the system, then you get maximum amplitude of oscillation. Okay, this is what resonance actually is. So let's just say, for example, we consider a case where you have a trolley that is held on a horizontal surface by means of two stretched springs. So this is your trolley, and then these are your springs on either side of it. So one end of your spring is attached to a fixed point, which is right over here. And then the other end of the other spring is attached to an oscillator, which is this one here. So this oscillator is the one that will cause horizontal oscillation of your trolley. So if you can imagine this, your oscillator will actually push and pull on your spring right over here. So when it pushes and pulls on your spring right over here, it also pushes and pulls on the trolley. So in a way, the oscillator here will actually cause an oscillation of your trolley. Okay, so here, what we'll say is that if your oscillator has a certain frequency, we call this the driving frequency because this is the frequency that is actually being applied to your system. Say your driving frequency is 50 Hertz, it will cause your trolley to oscillate with 50 Hertz too. If you change it to say 100 Hertz, your trolley will then change to oscillate at 100 Hertz. Okay, so here what we're interested to know is what happens when we go and increase the driving frequency from a low value to a high value. Say we want to increase the driving frequency. So what we do now is that we increase the frequency of vibration of the oscillator from a very low value, and then from there we want to see how does the trolley oscillate. Specifically, we want to find out is amplitude of oscillation. Okay, we know that as the trolley moves back and forth, left and right, it should have some amplitude of oscillation. Okay, x0 here. So what we're interested to know is when your driving frequency increase, what happens to the amplitude? So what you do is that you increase your driving frequency from a very low value to a high value, you measure the corresponding amplitude. Okay, so what you notice is that you get a very specific graph shape. If you were to plot the graph of variation of frequency of amplitude of vibration, if you were to plot the variation of frequency of the amplitude of vibration of the trolley, you will get something that looks like this. Okay, so this is a graph of amplitude versus frequency. Okay, this is the driving frequency or frequency at which trolley is made to oscillate. Okay, so this is the amplitude of oscillation of the trolley. Okay, so this graph of amplitude versus frequency here is typically called a resonance curve. Okay, we normally call this a resonance curve. All right, it shows you where would the system actually experience resonance. Okay, so say for example, I gave you a case where just now you started off from a frequency of 50 Hertz and then you increase to a frequency of 100 Hertz. And then let's just say you keep on increasing your frequency. Say maybe this is 120, this is 150, maybe this is 180. Specifically, at one particular frequency, your amplitude of oscillation will actually start to reach a maximum. So this one here, we can say this as A max now, the maximum amplitude of oscillation. So there will be one point in particular on your resonance curve where you see that your amplitude is maximum. This is the part where we say that your system is achieving resonance. Okay, So resonance will occur when your driving frequency equals your natural frequency. All right. So say for example, if my trolley has a natural frequency of 120 Hertz, I tell you just now that my frequency of my oscillator was increased from 50 Hertz upwards. Say I increase it all the way to 180 Hertz. There will be one particular frequency from 50 Hertz to 180 Hertz that will somehow coincide with my natural frequency. When my driving frequency coincides with my natural frequency, your system will oscillate with maximum amplitude. Okay, so what you can see from the resonance curve here is that initially your amplitude from here to here, your amplitude increase. But right over here, your amplitude is max. And then going further again, when your frequency increase, your amplitude starts to drop. What you're really interested in is this point here, where you reach maximum amplitude. That is where you have resonance. So resonance occurs when driving frequency equals natural frequency. All right. So recall that last week when I mentioned to you about free and forced oscillation, I told you that free oscillation tends to oscillate at its natural frequency naturally. Okay. Your natural frequency is readily displayed from a free oscillation system. But for forced oscillation, because it always follows the frequency at which your driving force is being applied, it doesn't readily display its natural frequency. But that doesn't mean that the system doesn't have natural frequency. It has its own natural frequency also, just that it's not freely shown for forced oscillation system. So in your case here, when you are talking about the trolley itself already has its own natural frequency, just that it's not readily shown. But somehow or another, when you go and increase your driving frequency from a low value to a high value, one of your driving frequency will now match your natural frequency. That's the point where your system oscillates at maximum amplitude. That's where we say that your system is undergoing resonance. Okay. So here in the notes, if you look at one of the statements, the amplitude oscillation of the driven system will increase to a maximum when the driving frequency from oscillator equals the natural frequency of the driven system. Okay, increases to a maximum is referring to this part here. Okay, so at resonance, you can say that system oscillates at maximum amplitude when driving force frequency equals the natural frequency of your system. Okay, that's the main thing to note from here. The moment driving frequency equals to natural frequency, your amplitude of oscillation will be maximum. Okay. Then after that, if you keep on increasing your frequency, your amplitude of oscillation will start to decrease. Okay. That's just one thing to note, but it's not that important. Okay, now regarding your resonance curve, you are supposed to know what are the effects of increasing the damping on your resonance curve. So increasing damping to a system that's oscillating tends to produce these three effects on your resonance curve. Number one, when you have increased damping, your whole graph actually becomes lower. Number two, your graph becomes flatter. Okay. Let me just note this. When your damping is increased, your graph becomes lower, your graph becomes flatter. So how do I look at it? You can just think of it this way. Say just now, the original resonance curve was this one. This one was where it was experiencing light damping. So when I go and increase the damping increase going downwards like this, where I go from critical damping. From light damping, I go to critical damping, and then subsequently heavy damping. You notice the curve tends to become something like that's shown in the diagram here. So it is actually becoming lower and it's actually becoming flatter. Okay, so when we say it becomes flatter, this one means something like this. If your original resonance curve was like this, okay, if you draw something like this, your graph is lower but not flatter. Okay, you see the entire red line is actually lower than the black line. We say that the graph is lower, yes, correct, but it's actually not flatter. It's actually sharper, if anything. It's not flatter here. So when we say it's flatter, we want something like this actually. So let me draw that same graph for you again. It's like this, but then we have something like this. Okay, so this one is lower graph plus it is flatter. Okay, you just look at the peak. Okay, the peak of your graph, you will be able to see then whether it's sharper or flatter. Okay, so in general, when you introduce damping, these first two criteria must be followed. Your graph must be lower and it must be flatter. Okay, there's also a third criteria when you introduce damping to your system, when you increase damping on the system, sorry. That one is that the frequency at which maximum response occurs also decreases. Maximum response here refers to the point where you get maximum amplitude. Okay, here if you increase damping, the frequency at which you're going to get maximum amplitude oscillation tends to shift to the left. So you see in your case here, for light damping, maybe I should use the corresponding colors. For light damping, your maximum amplitude occurs here, okay, or rather your resonance occurs there. For critical damping, your maximum amplitude or your resonance occurs here. And then for heavy damping, your maximum amplitude or resonance occurs here. So you notice that the frequency is actually decreasing when it concerns the point where you get maximum amplitude. All right, so that's why here we say the graph tends to shift to the left. Now the reason why we say that the graph actually shifts to the left is because of this. When you have increased damping, your object oscillates slower. Therefore, the time taken to complete one oscillation is longer. Therefore, period is longer, frequency is shorter then. That could explain why your frequency suddenly shifts to the left. Okay, but one thing to note here is this. When it comes to drawing your resonance curve to increase damping in your exam questions, the important ones to follow would be the first and second criteria. The third one is optional to follow. You can show it, you can choose not to show it. It will still be acceptable either way. Okay, so that's one thing to note. Okay, now all these resonance curves that you have here is showing damping present inside the system. What about if you do not have damping inside the system? If you do not have damping, how would the resonance curve look like? With no damping, your peak would actually be infinite. What we mean by that is that you look something like this. There's no limit to it. You don't see any limit to it. It just goes up, and then there's no end to it. So this one here is no damping. So this one has infinite peaks, or rather there's no limit to the peak. Okay, there's no limit to the peak, it's an infinite peak, so that is no damping. Okay, so that's what we mean by the resonance curve having damping. Okay, then we move on to the last part of your chapter, which talks about resonance examples. Now, resonance can be both useful and not useful. You need to know a bit of both. Now, let's just say, for example, what are the cases where resonance should be avoided? Okay, the easiest case to quote would be for the case of a building when it's subjected to an earthquake. Now, say for example, if you have a building like this, we know that it's actually resting on the ground. Okay, so when you have an earthquake, your ground shakes. Okay, so your ground shakes with a certain frequency. All right, so say for example, to make our analysis easier, we assume that maybe our ground is shaking left and right with a frequency of 1000 hertz now. Okay, so your ground shaking is actually also going to be shaking the building on top of it. All right, so it's correct to say that your ground is actually applying a driving frequency onto the building itself because your building is resting on top of it. So if the ground is shaking with a certain frequency of 1000 hertz, your building resting on top of the ground will also shake with the same frequency. The ground is applying a driving frequency onto the building. Okay, so that building is now shaking at 1000 hertz due to the earthquake. But the building has its own natural frequency. Say, for example, if our natural frequency is 1500 hertz. So if let's say our earthquake was causing a driving frequency of 1000 hertz, but our natural frequency is 1500 hertz, our building will still shake. Okay, that one is still okay. But what happens if necessary for one small period, for some period of time, our driving frequency suddenly changed to 1500 hertz? So in this case here, when your driving frequency suddenly becomes equal to the natural frequency of the building, what will then happen is that when Fd equals to Fn, you have resonance. Your building oscillates with the largest amplitude, or rather the maximum amplitude. So what then happens is that when it's oscillating at the largest amplitude, your building will actually break apart. Okay, so here in the notes, it was mentioned something like this. During an earthquake, frequency of the ground shaking may be the same as the natural frequency of your building, thus causing large amplitude oscillations. As a result of that, your building may collapse as the rigid concrete or brick structure around it breaks apart. So you've seen concrete or bricks before, you can't really bend it, right? Though if you try to forcibly bend it, it will break. So it's something similar here. Your building by right is supposed to be rigid. So if you trying to force it to oscillate left and right with very large amplitude, let's just say going towards the left here like this, or going towards the right here like this, it's going to cause the building to break apart. It's going to cause the building to collapse. Okay, so in order to prevent something like this from happening, to prevent your building from collapsing due to resonance, what they normally do is that they design the buildings so that the natural frequency is very much different than that of the frequency of the ground shaking during earthquake. So what we mean is that it could be something like this. Your driving frequency of earthquake, maybe say for the sake of discussion, is known to be between 1000 to 1500 hertz. So knowing this, what you do is that you purposely go and design your building, you make it higher, you make it shorter, you make it fatter, narrow, or whatever, so that your driving frequency becomes something else, say maybe 3000 hertz. So if let's say a natural frequency is 3000 hertz and then you have an earthquake, there's no way that your earthquake frequency will ever be the same as your natural frequency. So you avoid the possibility of your building actually collapsing due to very large oscillations during resonance. Okay, so that's one thing to note about resonance. Now, alternatively, other than changing your building's natural frequency, you can also build steel columns into the building so that your building is more ductile and can bend without breaking, and can bend more without breaking apart. So what this means is that you actually try to run steel beams into your building like this so that it can actually bend up, it can actually bend more without breaking. All right, so this is one example case where resonance should be avoided for the case of a building. Now the same can also be said for bridges also. Okay, so when you normally design a bridge, you do not want your bridge to encounter resonance. So a case in point would be for when you're talking about a suspension bridge. The picture over here shows you a suspension bridge. Notice that it seems to be twisting. All right, the bridge is twisting because of the effects of resonance. It's trying to twist or oscillate with maximum amplitude. So what we'll say is that generally, if necessary, you're looking at a suspension bridge, I give you a simplified cross-sectional area of your suspension bridge. Say it looks like this, for example, with a squarish shape, sorry, with a rectangular looking cross-sectional area like this. So when you have a bridge and then you subject the bridge to blowing wind, let's just say your wind is going in this direction. When wind encounters the bridge, if your bridge is squarish like this with no holes through it, what happens then is that when the wind hits the bridge, it can't flow over the top, it can't flow over the bottom. Instead, it flows head-on onto your bridge. So it flows head-on onto your bridge, then after that, it can't move through, it will just turn back. It hits and then it turns back. Okay, like this. All right. So this wind blowing back causes oscillation of bridge at a certain frequency. Okay, so when the wind hits the bridge and it's forced to turn back, it kind of causes oscillation of the bridge at a certain frequency. Okay, so say right now your wind is exerting a driving frequency, is causing oscillation of the bridge at a certain frequency. Let's just call this driving frequency of say 500 hertz. Same thing, is causing a driving frequency of 500 hertz. So again, your bridge has its own natural frequency. So if the natural frequency of your bridge is coincidentally 500 hertz, so in your case here, your bridge will actually oscillate with maximum amplitude. It will actually twist with a very, very large amplitude. So when it twists with a very large amplitude, your bridge will actually break apart and collapse. Okay. So here the note says when wind blows across the deck of a suspension bridge, the turbulent winds known as eddies are formed, can cause the bridge to twist and oscillate. This is what we call as eddies. Okay. This is your turbulent wind, which we otherwise known as eddies. Okay, but this term is not something that you will need to use in your exam, so you don't really need to bother to know so much about it. Just know that when wind blows across the bridge, it can't pass through, but it's being forced to turn back. So that kind of causes some sort of oscillating force at a certain frequency. Okay, so if your winds are actually causing oscillation equal to the natural frequency, your deck will start to undergo large amplitude oscillations and eventually breaks apart. Okay, so to overcome this, what they've done is that you design the bridge so that it's aerodynamic, so that wind can actually flow above and below without forming eddies. So what we mean from that is that rather than designing it with a squarish shape like this, you could somehow design it to be a bit trapezoidal like this, something like a hexagon cross-sectional area like this, so that when wind blows, the wind can actually just flow above and below your bridge. This one can flow above, this one can flow below. Okay, so this way you will avoid causing any kind of oscillation on your bridge. Okay, so this is another example where resonance should be avoided and how you actually overcome them. Okay, so next one is cases where resonance is useful. Okay, so for cases where resonance is useful, this one would be probably something that you guys would have learned in IGCSE before. Now, cases where resonance is useful is in your microwave oven. Okay, so how does your microwave actually work in the first place? You see, your microwave, say this one is your microwave, and then you have some sort of food that you want to heat up. Sorry, you have some sort of food that you want to heat up. Let's just say you have a plate of rice. Let's just say, for example, you have a plate of rice. Okay, so your plate of rice contains water molecules that are vibrating continuously. Okay, any food that you have has moisture in them. So when you have moisture, you have water. So when you have water, you have water molecules. So those water molecules are always vibrating. Okay, so they are vibrating continuously at their natural frequency. Okay, so they are vibrating continuously at their natural frequency. Okay, so the idea here is that when you go and put your food inside microwave, your microwave oven will emit microwaves. Okay, it will emit microwaves. All right, so the microwaves have a certain frequency. So this frequency of your microwave, you can think of it as your driving frequency. So in the event that you go and emit microwaves, which we consider as our driving frequency here, in the event that the driving frequency is equal to your natural frequency of your water molecules, your H2O molecules vibrate faster. Okay, the molecular Ke increase, therefore temperature increase, your food heats up. Okay, you've learned the relation between molecular Ke and temperature in ideal gas, where we tell you that mean molecular Ke is actually 3/2 kT, isn't it? So here, you're kind of relating to something from that. When your driving frequency, which is from your microwave, is equal to the natural frequency of your water molecules, your water molecules vibrate faster, they move faster actually, so they have higher Ke, the temperature will increase, your food will heat up. Okay, so that's what the notes here is actually trying to tell you. In the microwave oven, the frequency of microwaves emitted matches the natural frequency of vibration of water molecules in your food. So these water molecules start to vibrate faster, generating heat to cook your food. Okay, this is what causes your food inside a microwave to heat up. Okay, now the last part where we talk about a useful example of resonance, this one is actually no longer in syllabus. What is describing is actually no longer in your syllabus because it's relating to something from the communication chapter, which has been removed from your A2 for 2002 onwards. This is actually from a chapter called Communication. All right, where we tell you in general, for a radio or television, you have an electronic oscillator inside your radio or television that tends to oscillate at a frequency that matches the signal frequency that's to be received from your radio or television station. So this allows effective reception of your signals. What this means is something like this now. Let's just say that this is your TV, and then after that, we tell you that you have a TV station here. The TV station is emitting its program at a certain frequency. So this one is your kind of like your natural frequency or something like that. Your TV is supposed to receive the signal from your TV station. Okay, so it wants to capture the signal from your TV station. So when it wants to capture the signal from your TV station, it has something called an electronic oscillator inside. Okay, so you force your electronic oscillator to oscillate. It oscillates with a certain frequency. This is called a driving frequency here. You purposely change your driving frequency until it matches the natural frequency, or rather the frequency of your TV station. When your frequency of your electronic oscillator matches the frequency of your TV station, that's where resonance occurs. You will get effective reception of your signals. Okay, that's the thing that we're trying to tell you here. Okay, the easy way to think about it is that think of the signal from your TV station as natural frequency, and then think of the frequency of your oscillator as your driving frequency. You purposely change the frequency of your electronic oscillator so that it matches the frequency of your radio station, of your TV station. Then you will get effective reception of your signals. Okay, so that one should be okay. All right, so if this one is okay, then I just fill off everything. We're done with the concept part of oscillation. So the next thing that we'll just do is mostly on your past years. Okay, so let me just clear everything off. Okay, now for oscillations, you can have a look at, say, page 4 of your worksheet. Okay, page 4 of your worksheet. Have a look at page 4 of your worksheet. This is November 15 P41. So, page 4, distinguish between free oscillation and forced oscillations. Okay. Now, free oscillation is when the body oscillates with no external forces applied. Okay. I mentioned to you last week that when you're talking about free oscillation, an easy way to understand it is to say that the system oscillates after being given an initial disturbance. Okay. Isn't it? So that definition here doesn't really come out that often in your marking scheme. Instead, they like to use this definition instead. They say that the body oscillates with no external forces applied, which is kind of true, you see. What I mean by that is that for free oscillation, the body oscillates after being given an initial disturbance. So when it oscillates, there are no longer any forces acting on it. Okay, that's why they say this. free oscillation is when your body oscillates with no other external forces applied. Okay, the one that I taught you last week was the body oscillates after being given an initial disturbance. But this one usually is not inside your marking scheme. Instead, this other one is more common inside your marking scheme. The body oscillates with no external force acting on it. It is true, okay? After you gave it an initial disturbance, you're no longer applying a force on it. So it's correct to say it is oscillating with no external force, okay? So that is for free oscillation. Now for forced oscillations, forced oscillation is where the body can only oscillate when an external periodic force is applied. It only oscillates so long as you keep on applying a force onto it. Okay, so that is for this case. All right, then if you're okay with that, then we move on to part B. Okay, so let me just clear off everything. Okay, I don't need to clear off anything, no need to clear all those things for now. Now, if you look at part B, a trolley is held on a horizontal surface by means of two stretched springs, as shown. One spring is attached to a fixed point, and then the other spring is attached to an oscillator that causes horizontal oscillation of your trolleys. This is actually the exact same diagram and description that I actually put inside your notes just now. Okay, so your oscillator is now vibrating at constant amplitude of vibration. The frequency of vibration of your oscillator is gradually increased from a very low value. And then what they told you here is that the variation with frequency f of the amplitude of vibration of the trolley is shown below. Okay, so I really described how the system works in the notes just now. What you're doing now is that you're increasing the frequency of your oscillator, which in turn causes the trolley to oscillate at the same frequency of the oscillator. So you increase the frequency of your oscillator, and then you go and find out the amplitude of oscillation of your trolley, and you produce the graph that you see below, which is a graph of amplitude versus frequency. So this frequency f is the frequency, if you want to think of it, this one is the frequency of your trolley, which is in turn equals to the frequency of your oscillator, which is in turn, let me write it out properly, is equal to the frequency of your oscillator, which is in turn your driving frequency. Okay, so this is what you have here. This FD is referring to that. It is the frequency of your trolley. It's also the frequency of your oscillator. It is actually your driving frequency here. Okay. So the next part of the question in the next page mentions this. Use the graph to state and explain the value of natural frequency or vibration of the trolley. By looking at the graph, how do I know what's the natural frequency of the trolley? So you look at the graph, you notice that this point here is where you have maximum amplitude. Okay. Now, when you have maximum amplitude, that one is where resonance is occurring. And when you have resonance, driving frequency must be equal to the natural frequency of your system. So here at maximum amplitude, you look at what is the frequency that corresponds to your driving, you look at what's the frequency that corresponds to the maximum amplitude. You will notice that it is actually 2.1. Okay, so this is where driving frequency of your oscillator must be equal to your natural frequency of your trolley. Okay, that's how you would deduce it from your graph. Where you have maximum amplitude, that's where you have resonance. Where you have resonance, that's where driving frequency equals to natural frequency. So whatever value of your driving frequency here is actually the natural frequency of the system. In your case, it's the natural frequency of your trolley. Okay, so how you word your answers is something like this. You just say something like this where you mention at resonance, trolley vibrates at maximum amplitude when driving frequency equals natural frequency of trolley. Therefore, the natural frequency is 2.1 Hertz. Right, so this one is about 3 marks. The marking scheme gives you an allowance to the natural frequency. It could be anywhere between 2.08 to 2.12 Hertz. Okay. So this one is how you answer that question. Okay, then after that, we move on to the next part, part 2. Okay, if you're okay with that, I'll move on to part 2. For the graph, state whether are there any frictional forces acting on the trolley. Okay, how do I know whether frictional forces are present? Now, frictional forces causes damping. Okay, if you have frictional forces, air resistance, or any kind of resistive forces, they tend to cause damping. All right. So how do I know right now by looking at the graph whether are there any frictional forces? Or in other words, whether do I know are they damping? So it was mentioned to you just now in the notes when it came to the resonance curve. When you have no damping, the peak is infinite, meaning to say it should be something like this. This is what no damping actually means. So looking at the graph, do you see your graph having an infinite peak or no limit to your peak? No, right? So we say something like this now, the amplitude is not infinite, so frictional forces are present. Okay. Or you could actually kind of replace it with this now. The peak is not infinite, so frictional forces are present. Okay, there's a limit to your amplitude, there's a limit to your peak, so frictional forces are actually present here, in other words. Okay, so because the amplitude or peak is not infinite, so frictional forces are therefore present. All right, so far so good with this. All right, then after that, one thing I want to go through with you is this. Right, so before we go on to part C, there's just one thing I want to mention here to you. Now, for the case that's been described to you here, they tell you that your trolley is attached to your oscillator. So the oscillator vibrates with constant amplitude of vibration, and then the frequency of vibration of the oscillator is gradually increased from a very low value to a high value, which in turn gives you the graph below here. Now, in this circumstance here, your trolley is forced oscillation. Okay, your trolley is, in the case that has been described here, where your trolley is attached to your oscillator, your trolley right now is under forced oscillation. Okay, it only oscillates so long as the oscillator applies a periodic force on it. Okay, so this case here is still where you say that your trolley is under forced oscillation. It only oscillates so long as so long as the oscillator applies a periodic driving force on it. If you look at part C, the one that you're looking at right now, you notice this. They tell you your oscillator is now stopped. Okay. Then after that, they tell you the trolley is given a horizontal displacement of 4.7 meter along the line of the springs, and then the trolley is released. Now, when they tell you your oscillator is now stopped, and then they then mention that they give your trolley an initial displacement and then release it, your trolley will still oscillate, but this time it becomes a free oscillation system. Okay. So there's a difference between what you see in B and C right now. B, it was still oscillating under forced oscillation because your oscillator is directly connected to it and it will switch on to cause the oscillation of your trolley. For C, the oscillator is switched off. So what they really mentioned here is that your oscillator is now switched off and they purposely displace it 4.7 centimeter towards one side before releasing it. So logic will tell you if your trolley is now connected to springs on either side, the moment you release it from 4.7 centimeter from one side, your trolley will actually now oscillate left and right. Okay. So when it oscillates left and right now, after your initial disturbance of 4.7 centimeter, it is actually free oscillation. Okay. So one thing to note from here is this: since it is now a free oscillation system, whatever frequency that your trolley is oscillating ought to be your natural frequency, which you actually found out from the question above here. Okay, your natural frequency here is supposed to be 2.1 hertz. Your trolley is now oscillating with 2.1 hertz. Okay, and then another thing that you can kind of see from the second statement is that since your trolley is given initial horizontal displacement before it's being released, whatever amplitude of oscillation that you have will never be higher than 4.7 centimeter. Okay, this one I explained in detail last week, I believe. So I mentioned to you, whatever displacement you give your system, your amplitude will only go up to as much. It can never be higher than whatever you put in because of conservation of energy. Okay, so when they tell you your initial displacement, horizontal displacement is 4.7, you can just think of it as your amplitude as 4.7. Or in other words, maximum amplitude is 4.7. Okay, it can never go higher, but it can go lower if you have damping. All right. So here, why do you need to know all this is because of what they say after that. Use the information from figure 4.2 to estimate the maximum speed of the trolley. Okay, how do you find out the maximum speed of your trolley? You already learned from simple harmonic motion that Vmax is actually omega x naught. And omega in turn is 2 pi f. So it's 2 pi f x naught for Vmax now. Okay. So that's why you get the equation that you're seeing on the screen right over here. So Vmax is omega x naught, 2 pi f x naught. So it's 2 pi and then multiply with f. So what value of f should I use? As I mentioned to you, because it's a free oscillation system, you are oscillating with natural frequency. You should be using a value of 2.1. And then x naught is your amplitude. What value should you use? You should be using 4.7 because this is by right your amplitude. It will never be higher than your initial displacement. Okay, so summing everything, you will eventually get the value as 0.62 meter per second. Okay, this is your answer for this particular question. All right, so far so good. Okay, so that one is okay. Let me see whether this, I can just, is there another question here? No, there's no question here. Right, so if that one is okay, then maybe we go on to another one. Let me see what's the next question. It is actually on the page 13. Okay, maybe we try to do this. Okay, have a look at page 13. We'll just do this one before we take a short 10 minutes break later. So have a look at page 13. This is June 16 P42. Okay, so June 16 P42. Right, so in your question here, wait, sorry, I think wait now my screen share suddenly went haywire. Okay, now I think you guys can see it. Okay, now for this particular question, a metal block hangs vertically from one end of a spring. The other end of the spring is tied to a thread that passes over a pulley and is attached to a vibrator. Okay. So here, the important thing to note is that one end of your spring is actually attached to a vibrator or an oscillator. Okay, they mean the same thing as shown in the figure right below here. All right. So here, they tell you the vibrator is switched off. And then after that, a metal block of mass 120 gram is displaced vertically and then released. The variation with time t of the displacement while the block form its equilibrium position is shown here. All right. So if you look at the system right now, this is your spring. This is your block attached to the spring at one end. And then the other end of the spring is attached to an oscillator or vibrator. But here they specifically told you your vibrator is switched off. And then what they did was that they merely displaced the block of a certain mass before releasing it. So logic again will tell you your mass will actually just oscillate up and down. In your case right now, when your mass is oscillating up and down, it's actually under free oscillation system. Your vibrator is switched off. It is actually not causing the oscillation of the block itself. Okay, so it cannot be forced oscillation. Instead, you gave it an initial disturbance and then it started oscillating by itself. This is free oscillation. Okay, so the oscillation of the block is what you see under the graph below. All right, so whatever frequency that you have here must be natural frequency because you are under free oscillation now. Okay, so this one here, you can actually just make a mental note. This one is oscillating at natural frequency due to system being free oscillation now. Being free oscillation system. Okay, it's oscillating at natural frequency due to system being free oscillation system. Okay, now for the vibrations, the block, calculate the angular frequency omega. We want you to find out what is omega here. Omega here refers to the angular frequency, which by now you should know is just simply either omega equals to 2 pi f or omega equals to 2 pi over t. It'll be easier to use the second one because you can easily find out your period here. This is t equals to 0.6 seconds. Okay, so omega is 2 pi over t, 2 pi over 0.6, you get 10.5 radians per second. All right, so this is for this particular question. All right, so if this is okay, then we move on to the next one. Okay, now what is the energy of the vibrations? Okay, what is the energy of the vibrations? So here, notice this. Your amplitude remains constant throughout, right? This one you can see that the amplitude is constant throughout. So this means there's no damping no energy loss. The energy remains, total energy, sorry, I should have probably written this. The total energy remains constant throughout. Okay. So from the graph that you see here, because you see that the amplitude is constant, that tells you that there's no damping, no energy loss. The total energy here is actually constant throughout. Okay. So you just, from here, what you can actually just say is pick any point to find total energy. Since the total energy remains constant here anyway, okay, so there's no need for you to be you don't need to like go and see what suitable point to pick. Just pick any point to find the total energy. You could pick this point A to find total energy. You can pick this point B to find total energy. Total energy for your case, if you learn the simple harmonic portion 1 or 2 lessons back, is Ke max is half m omega square x naught square. Okay, so you really just need the amplitude value to find the total energy. So in your case, any of these amplitude values would actually do. Okay, right? You don't need to pick any particular point. Just pick any of the amplitude values and you should be able to get your answer. Okay, so if you do this, this is what you get. Now let me just zoom in. So your total energy is Ek max half m omega x naught square. So half times the mass, which is 120 grams, changed to kg. Your angular frequency you already found in part 1 previous page. Your x naught, you can read it from your graph. It's actually 2 centimeter. Remember to change it to meter and remember to square it. So eventually you get 2.65 times 10 power minus 3. Okay, so this is your answer. Okay, so this is your answer. Okay, now for part B, let's have a look at part B. Before we call it, we should take a short break. Now the vibrator is switched on. All right. If previously the vibrator was switched off and it was a free oscillation system, now vibrator is switched on. Your system is now actually going to be oscillating, but it's a forced oscillation system now. All right. So they tell you that the frequency of vibration of your vibrator is varied from 0.7 F to 1.3 F, where F is the frequency of vibration of the block in A. All right. Your block in A over here is where vibrator was switched off. It is vibrating freely. It's a free oscillation system. Your frequency then is your natural frequency. Okay. So here the question says this: the frequency of vibration is varied from 0.7 F to 1.3 F, where F is the frequency of vibration of the block in A. So the system in A was actually vibrating at natural frequency because it was a free oscillation system. So this F now, think of it another way, is actually your natural frequency right now. Okay. So they are saying that they're changing the frequency of your vibrator from 0.7 F to 1.3 F. And then from there, they ask you to complete the figure below to show the variation of frequency of amplitude, to show the variation of frequency of the amplitude of vibration, and then label this line A. Okay. So this one is graph of amplitude versus frequency. Your graph shape should look like this. Okay. highlight it for you. Your graph shape should look like this. Okay, it's this one. All right. So your peak, where you get maximum amplitude, must correspond to where driving frequency equals to natural frequency. In your case, it should be at F here. This is where driving frequency equals to natural frequency. Okay. So this is your resonance curve for your case right now. All right. So when your driving frequency equals to your natural frequency, or in other words, equals to F, as defined by your question above, this is where you get maximum amplitude. All right. So that one is for this. Okay, so that one is for part B. Now we look at part C. Okay, part C, let me just find two from here. Okay, now you read the subsequent question in part C. They mentioned this. Light feathers are now attached to the block to increase air resistance. The frequency of vibration is once again varied from 0.7F to 1.3F, and the new amplitude of vibration is measured for each frequency. On the same figure, draw a line to show the variation with frequency of the amplitude of vibration. They're basically asking you to look back at the same graph and draw the new curve when you have increased air resistance as a if due to the, draw the new curve when you consider that there's now increased air resistance due to light feathers being added to the block. Okay, so what they basically mean from here is that for your diagram here, they just attach feathers to your block. This one increases air resistance. Now, when your air resistance increase, your damping increase. Because you have more air resistance, you cause more losses in energy, so your damping would increase. Your oscillation will actually lose more energy as a result of the damping. So just now I mentioned to you, when it comes to resonance curve, when you have increased damping, your curve generally needs to follow three criteria. Number one is that your graph must be flatter. Number two, number one is that your graph must be lower than before. Number two, your graph must be flatter. And then number three, the frequency at which you have resonance or maximum frequency should be shifted to the left, right? It's following what I mentioned in the notes in page 3 under this part. Okay. So with increased damping, the whole graph must be lower, the graph must be flatter, and the frequency at which you get resonance should be towards the left. Okay, but I mentioned that only the first two is important, but the last one is optional. You could choose to show it, you could choose not to show it. Okay, if you choose not to show it, you can just maintain it at the original frequency. Okay, rather than shifting to the left, you can actually just maintain it at the same frequency. Okay, so you can actually see it being reflected in the marking scheme. Actually, the marking scheme actually did reflect it. Okay, so just now I told you that this one is A. The new line should be B, label B. You look at what the marking scheme said on in red around your diagram. They say that your peak line must always be below peak line A. The graph must always be lower, in other words. And then the second thing they mentioned is that your peak not as sharp, meaning to say is flatter peak, and at frequency or peak in line A, meaning to say you could have drawn it like this. where your peak is right over here instead, or slightly less than the frequency peak in line A. Meaning to say you could have just drawn it like this, where the frequency at which you get your peak is slightly to the left. Okay, that's why you see I mentioned to you, it's actually optional to follow because there's the word or. You either put the frequency at the previous frequency or slightly less than the previous frequency. Okay, so either way is fine. It's up to you. All right. Yeah, there's one typo error in the writings here. Here they say light feathers are attached to the block to increase air resistance, but then I go and say here damping is introduced in the system, right? This is actually not a correct thing to use. It's more correct to say damping is increased. Damping is increased in system. Okay, damping is increased in the system, not damping is introduced in the system. Damping is increased in the system. Okay,